Okay, in this video we're going to talk about the introduction to electricity. Electricity, movement of electrons, a visible force that provides light, heat, sound, and motion. Electricity at the atomic level. Elements, well, those are the simplest forms of matter. Atoms are the smallest piece of an element containing all the properties of that element. Components of an atom. Well, there's the nucleus, that's the center portion of an atom containing protons and neutrons. Protons, those are the positively charged atomic particles. Neutrons are uncharged. The atomic number is equal to the number of protons in the nucleus of an atom, and that identifies it. How many protons in this nucleus? Well, 1, 2, 3, 4. Electrons, this is what has to do with electricity. Negatively charged particles. Electron orbitals, orbits in which electrons move around the nucleus of an atom. Valence electrons, these are really important. The outermost ring of electrons in an atom. So let's look at all the different electron orbitals. The left column is the orbit number. The right column is the maximum electrons that it can hold. So 1, 2, 3, 4, 5, 6 orbitals. In this particular one, it has 8 valence electrons. The orbits closest to the nucleus fill first. Electron orbits. Atoms like to have their valence ring either filled with 8 electrons or empty with 0 electrons. How many electrons in the valence orbit? I count 1. So, is copper a conductor or an insulator? If you answered conductor, you're right, because it wants to get rid of that electron, and that is what makes electricity. Conversely, let's look at sulfur. How many electrons does it have in its valence orbit? 1, 2, 3, 4, 5, 6. Good insulator or conductor? If you answered insulator, you're right. It has too many, it's almost satisfied in its outermost shell, in its valence shell, so it'd be hard to get rid of all those electrons. Whereas copper had 1, it's very easy for it to get rid of it. Electron flow. An electron from one orbit can knock out an electron from another orbit, just like I was talking about. When an atom loses an electron, it seeks another to fill the vacancy. Electricity is created as electrons collide and transfer from atom to atom. That is electricity. When one bounces and strikes another and strikes another and strikes another, it's transferring energy, it's transferring electricity. Conductors. Electrons flow easily, like we said. Insulators, electron flow is difficult, like that sulfur atom. 1 to 3 valence electrons, 5 to 8 valence electrons. Examples, silver, copper, gold, aluminum. Examples of insulators, mica, glass, quartz, and sulfur. Good conductor on this picture would be the end of the pliers and the wire. Good insulators are the plastic sheath around that wire and the plastic around the red plastic around those pliers for obvious reasons, maybe not to get shocked when we're working on electricity. All right, some terminology. Properties of an electrical circuit include voltage, V. Voltage is measured in volts. It's commonly used capital V to identify it. Current is measured in amps. We commonly use A, although sometimes you'll see a capital I as well. Resistance is measured in ohms, and we use the omega ohm symbol. Okay, let's talk about current. Current is the flow of electric charge. It's measured in amps or amperes. You can think of it as, let's think of a water system or a plumbing system. There's a tank or battery, pipe or wire. When the faucet or the switch is off, is there any current? Is there any flow? Well, no, there isn't. When the faucet switches on, is there any flow or current? Well, yes, there is. And so think of current similar to water. Current in a circuit. When the switch is off, there is no current, right? When the switch is on, there is current. Conventional current versus electron flow. What we usually think of in engineering, there's kind of two trains of thought versus science or engineering. Because this is an engineering class, we are always going to assume that current is flowing from positive, leaving and coming back, returning to negative, not the other way around. And let me read through this as well. The direction that the current flows does not affect what the current is doing, thus it doesn't make any difference which convention is used as long as you are consistent. Both conventional current and electron flow are used. In general, the science disciplines use electron flow, the one on the left, whereas the engineering disciplines use conventional current. Since this is an engineering course, we're going to be using conventional current, leaving from positive, returning back to negative. Okay, voltage. Again, our water example, our plumbing example, force or pressure that causes current to flow, it is measured in volts. When the faucet is off or the switch is off, is there any pressure or voltage? Well, yes, there is pressure pushing against the pipe, tank, and the faucet. When the faucet switches on, is there any pressure? Yes, there is still pressure. Pressure voltage pushes flow. Remember, it pushes the current through the system. Voltage pushes current. Voltage in a circuit. The battery provides voltage that will push current through the bulb when the switch is on. All right, resistance. The opposition of current to flow measured in ohms. How could we create some resistance in this plumbing example? What would cause resistance in a pipe? What if we threw a rock in there? If we threw a rock in this pipe, that would definitely hinder or slow down our flow or our current. Flow or current would decrease. Resistance in a current. Resistors are components that create resistance. If I place a resistor in this current, it will reduce the current, causing the bulb to become more dim. Let's discuss measuring. Measuring voltage. We'll set the multimeter to the proper voltage range. Notice this is a DC current, DC battery, right? Not AC, which would be what you would find in your house. So DC current, we set it to 20. We always set it with the appropriate setting is just above what you think you're going to be measuring. For example, a 9-volt battery, well, the lowest setting is 20. We don't want it at 200 or 600. We'll set it at 20. And then we'll measure across our component. This is what across means. Our leads are going to be measured across this battery, or across the switch, or across the resistor, or across the LED. Multimeter, an instrument obviously to measure the properties of an electrical current, including voltage, current, and resistance. Current, we set it to the appropriate range. Current flow must go through the meter. Notice we remove a wire. The current will then flow through the switch, through this red lead into the meter, out the black lead, out the black lead, and then continue its path through the meter. Resistance, we'll set it to the appropriate range. Measure across the component, but power is off. Notice, power is off, and then we will measure across. Okay, let's discuss Ohm's law. Current in a resistor varies in direct proportion to the voltage applied to it and is inversely proportional to the resistor's value. Mathematical relationship between current, voltage, and resistance. If you know two of the quantities, you can solve for the third. Quantities, voltage, current, resistance. Abbreviations, VIR. Units, volts, amperes or amps, ohms. Symbols, V, A, and our omega symbol. VIR, I equals V over R, or R equals V over I. There's a better way to remember that. If you draw out circle T, so see the circle and then the T, and you write VIR. You can do this for any equation that has something equals has three variables, is what I'm trying to say. You can do this for any equation that has three variables. You cover for what you want to solve for. So if I want to solve for V, imagine covering V, multiply I times R. If I want to solve for I, put my thumb over I, and then I know that I need to do voltage divided by resistance. Same for R. Okay, let's do some examples. The flashlight shown uses a 6-volt battery and has a bulb with a resistance of 150 ohms. When the flashlight is on, how much current will be drawn from the battery? First thing I do is draw a schematic. Here's my battery. Here's my resistor. And it's asking for current. So they did circle T just with a triangle, same type thing. So I put my thumb or my finger over I, so then I know it's going to be volts divided by resistance. I equals V over R. I equals 6 volts over 150 ohms equals 0.04 amps or 40 milliamps. Let's talk about some conversions. Now's a good time to do that. You may want to write this down. Let's mention milliamps since we just did a problem with current and amps. 1 amp is equal to 1,000 milliamps. Milliamps, as you can see here, is abbreviated little m, capital A. Another one is microamps. 1 microamp, and microamps are abbreviated little u, big A. 1 microamp equals 0.000001 amps. I'll repeat that again. 1 microamp equals 0.000001 amps. And then there's one other one we need to know. 1 ohm is equal to 0.001 kiloohms. Kiloohms. That's with a lowercase k and then the ohm symbol. Okay, let's talk about circuit configuration. Components in a circuit can be connected in one of two ways. Series circuit, components are connected end to end. There's only one way for the electricity to flow, just like Christmas tree lights. If one goes out, they'll all go out. A parallel circuit, both ends of the components are connected together. There are multiple paths for the current to flow, just like your house. If a light bulb goes out in the bedroom, well, I hope that your microwave doesn't go out in the kitchen, right? Because your house is wired in parallel. Kirchhoff's voltage law. The sum of all voltage drops or voltages in a series circuit equals the total applied voltage. The sum of all the voltage in a series circuit is equal to the total voltage. Kirchhoff's current law. The total current in a parallel circuit equals the sum of the individual branches. This can be summed up in, you might want to write this part down. Let's do series again. In a series circuit, voltage divides and current is the same. Voltage divides, meaning, just like it said, the sum of all voltage is equal to the total. And we're going to do an example of this in a minute. So in a series circuit, voltage divides and current is the same. Current is the same everywhere throughout the circuit. In a parallel circuit, current divides and voltage is the same. It's just the opposite. In a parallel circuit, current divides, voltage is the same. Series. Circuit that contains only one path, we just mentioned that. If a path is open anywhere, current stops flowing. Characteristics of a series circuit: the current flowing through every series component is equal. Remember, we said in a series circuit, current is equal. Total resistance is equal to the sum of all the resistance. Sum of all voltage drops, or voltage, is equal to the total voltage in the circuit. Remember, that's Kirchhoff's voltage law. Okay, we're going to do some practice with this in a minute. Let's see. Series circuit. For the series circuit shown, use the laws of circuit theory to calculate the following. I want to know total resistance, the current flowing through each component, the voltage across each component, and use the results to verify Kirchhoff's voltage law. Okay? So here's my schematic. Total resistance, let's do that one first. RT equals R1 plus R2 plus R3. Simple enough. 220 ohms, 470 ohms, 1.2 kiloohms. I like to convert this number into the base unit, or ohms, so this would be 1200 ohms. When you add that together, you'll get 1900 ohms, or 1.9 kiloohms. Doesn't matter what unit you put. Current through each component. Well, remember Ohm's law? Current is voltage total. If I want current through each component, I need to find out current total equals voltage total over resistance total. Current total equals 12 volts, see? 12 volts over resistance total, we just found that out, 1.9 kiloohms, equals 6.3 milliamps. Well, what would have happened if I had used 1900 instead of 1.9? Well, then I would have gotten amps, not milliamps. Since it's a series circuit, there's no math to do. Remember, you wrote down in a series circuit, voltage divides and current is the same. Current is the same. So if I find current at one place, just like we did here, it is the same everywhere. It's the same here, it's the same here, it's the same everywhere. Voltage across each component. Remember, voltage equals I times R. Voltage equals I times R. The reason these ones are here is what they're trying to say is at resistor 1, at resistor 2, and at resistor 3. Voltage at resistor 1. Well, current is the same. Remember, 6.349 milliamps times 220 ohms equals 1.397. Current or voltage at resistor 2, 6.349 times 470 equals 2.984 volts. At resistor 3, 6.349 milliamps times 1.2 kiloohms, 7.619 volts. If I add the voltage at resistor 3 and 2 and 1, I better get what? I better get what? The sum in a series circuit, voltage divides and current is the same. Voltage divides, meaning when I add these up, I better get 12. See? 1.397 plus 2.984 plus 7.619 equals 12 volts. A great self-check. You can never get these wrong. Okay, let's do parallel circuits. A circuit that contains more than one path. If a component is removed, then it is possible for the current to take another path to reach other components. If I remove one light bulb, the other one's still going to stay lit. Okay, characteristics of a parallel circuit. Just like we said earlier, current divides voltage is the same. Current divides voltage is the same. Another thing we need to realize is this equation right here. R total resistance total is not like parallel, or not like a series circuit. Our total equals 1 over each resistor, and then you add those up. This is very important. And this is just saying what we already said, current divides. Okay. So in this one, we're going to find total resistance, voltage across each component, current flowing through each component, and we're going to verify Kirchhoff's law. Let's do total resistance. It's not like a series circuit. Remember, here's our equation. Fill it in. 470, 2.2, 3.3. I'm pulling that from right here. I get 346.59 or 350 ohms. Let's talk about this for a second. 346 or 350. In electricity, you need to get used to a range. I know that may irk some of you, but it's normally a range of values. That's why they did this 350 here. Electricity isn't perfect. You're not going to get a resistance of exactly 346.59. You might measure it later and get something different. So electricity is commonly used as a range of values. All right, voltage, no math needed. Why? Because it's a parallel circuit. Voltage is the same. You know that it is 15 volts. Okay, current through each component. Remember, here's Ohm's law. Current equals V divided by R. Current equals V divided by R, 15 over R1. Now, remember, we said that current divides, so we're going to have to find the current at each resistor. And that's what they're doing here, here, and here. When I add these up, I will get the total current. Also, I can solve for total current by doing current total equals voltage total, I know that, resistance total, I know that, and then I get 43 milliamps. Or if you add these up, you'll also get 43 milliamps. That's just verifying it. Combination circuit, contain both series and parallel. What would happen if you removed light 1? So think about, you removed light 1, what would happen? What about 2 and what about 3? Electrical power. Electrical power is directly related to the amount of current and voltage within a system. Power is measured in watts. P equals I divided by V. We'll go more into this later in class. We're going to do an activity with a winch, and we'll go into this more detail in class.